Hello, Marine Gurukul Online Academy has launched a number of modules to support the students in learning and passing their certificate of competency examinations. For our schedules and updates, you may keep watching our YouTube channel. For any further help and support or information, please write to us on marinegurukul@gmail.com. Welcome to Marine Gurukul video series. In this video, we shall discuss how the different hydrostatic particulars of a vessel change with the change in draft or change in displacement. Besides learning how different hydrostatic particulars behave with change in draft or displacement, this video is also aimed at helping the students to answer some of the questions in the certificate of competency exam, like how do the following particulars change with the change in vessel's draft? These are some of the questions taken from past MMD exams, MCTC, TPC, LCB, and KM. Similarly, there was another question, explain how the values of the following parameters change with the change in vessel's drafts, KMT, LCB, MCTC, and LCF. So this video is also aimed at covering the answers to these questions. To answer this question on how does a hydrostatic particular varies with increase in ship's draft or displacement, it is essential to know and understand the following about the concerned hydrostatic particular. Its definition, how is it defined? Is there any formula associated with it? And the factors or the parameters affecting that particular hydrostatic parameter. Now, once we know these things, we can analyze the effect of change in draft or displacement on the basis of above information. Thereafter, we can draw a graph depicting the effect for a normal ship-shaped vessel. The hydrostatic curves of any ship, please understand, would depend on the hull form of the vessel. Now, hull forms are vessel specific. So, how exactly a particular hydrostatic parameter would change with draft or displacement shall slightly vary from ship to ship. In the discussion, for the sake of discussion in this video, we have used the hydrostatic curves and hydrostatic particulars of MV Hinship, which would in all likelihood resemble with the hydrostatic curves of a normal ship-shaped vessels. Exceptions could always be there, especially in view of now larger vessels with very high flare of the bow, with flattened stern, and all these parametric changes in the size and the proportions of the ships would obviously have an effect on the curves. But yes, whatever are the hydrostatic curves of MV Hinship, a normal vessel's hydrostatic curves would more or less behave the same way. Now, here on display are the hydrostatic tables of MV Hinship. I have put them here so that you don't need access to the hydrostatic booklet. So these are the particulars basis which the curves shall be drawn and discussed as the video progresses. These are the hydrostatic curves of MV Hinship. The sheet is contained in the stability booklet that you have in your possession and which you are allowed to take to the examination center. On the y-axis is the draft. On x-axis are the scales, but the scales are different for different parameters. They are given here, which probably you can't make out from here, but it's okay. Please understand there are different scales for different particulars because the units are also different. And then we have, this is the curve for displacement. This is the hydrostatic curve for TPC. for MCTC, for LCB, longitudinal center of buoyancy, for LCF, longitudinal center of flotation, KB or the vertical center of buoyancy, KMT, distance of transverse metacenter from keel, and lastly KML, distance of longitudinal metacenter from the keel. So these will be the curves used to basically describe the effect of draft on various hydrostatic particulars for a normal ship-shaped vessel. Effect of draft on displacement and vice versa, effect of displacement on draft. By law of flotation, we know displacement of a ship is equal to its volume of displacement multiplied by the density of the water in which the vessel is floating. And how much is the volume of displacement, or what is volume of displacement? It's the same for an intact vessel as her underwater volume. Therefore, displacement for an intact vessel becomes underwater volume multiplied by the density. Thus, the volume of displacement which we know increases with the increase in draft. And vice versa, you reduce the draft, the volume of displacement will reduce. Therefore, what do we see from here? The displacement of the ship is directly proportional to its draft, or the draft is directly proportional to displacement. And for normal ship-shaped vessel, the graph can be represented like this. You have the displacement on the x-axis in tons, you have the draft in meters on y-axis, and as the draft increases, the displacement increases. These values are on x-axis and draft are typically for MV hinge ship, but this is how the displacement of more or less every ship would change with the change in draft. Effect of draft or displacement on TPC. What is TPC? Tons per centimeter. What does it denote? It is the weight in tons required to cause an immersion or emmersion of 1 centimeter. TPC formula is water plane area divided by 100 into the density of the water in which the vessel is floating. Now, therefore, TPC, you can see from the formula, is directly proportional to water plane area. Based on how the water plane area of a typical ship-shaped vessel varies with draft or displacement, the change of TPC with draft or displacement can be shown in the graph as follows. On x-axis, we have TPC in tons per centimeter. On y-axis, we have draft in meters or displacement in tons, and it varies something like this for MV hinge ship. You can see this broken line here means the scale is from here. So basically 20 tons per centimeter, 30 tons per centimeter. These values are typically for MV hinge ship. But what do you see? Look at the graph. As the draft initially increases, the TPC is increasing, but the rate of increase reduces. The rate of change has reduced, but yes, with the increase in draft, the TPC typically increases with the rate of change, of course, gradually reducing and coming down. Effect of draft or displacement on MCTC. MCTC stands for moment to change trim by 1 centimeter. MCTC is the trimming moment in ton meter required to cause a change in trim by 1 centimeter. MCTC formula is it's W into GML divided by 100L, where W is the displacement, GML is the longitudinal metacentric height, and L is the length of the vessel. Now GML will be equal to KML minus KG, and KML in turn is equal to KB plus BML. So GML becomes equal to KB plus BML minus KG. Therefore, how does MCTC change with change in draft or displacement will depend upon displacement, KB and BML, their behavior with the change in draft. Based on the cumulative effect of change in displacement, KB and BML of a typical ship-shaped vessel like MV Hinship, the change of MCTC with draft or displacement is as per the following graph. We have MCTC on the x-axis, draft on y-axis. We have this continuation showing that the scale does not start from 0. It starts from here. This is 150, this is 225 ton meter. And when we plot the values of MCTC of MV Hinship, we find the graph coming like this. Again, what does it show? As the draft increases, MCTC increases, but the rate of increase again coming down with the increasing draft. So this is how typically the MCTC of a ship-shaped vessel will change with the change in draft or change in displacement. Effect of draft or displacement on KB or the vertical center of buoyancy. KB is the distance of center of buoyancy from keel. Center of buoyancy is the geometric center or the centroid of the ship's volume of buoyancy. What is volume of buoyancy equal to? Volume of buoyancy is equal to or is same as volume of displacement. So thus for an intact ship, the volume of buoyancy as well as volume of displacement, they are both equal to underwater volume. Thus, as the draft or displacement increases, the KB of a ship increases. For normal ship-shaped vessel, as a thumb rule, it is slightly more than half the draft. For a typical ship-shaped vessel, the change of KB with draft or displacement is as in the following graph. On x-axis, we have KB in meters. On y-axis, we have draft in meters or displacement in tons, whichever we want to consider. And this graph shows how the KB would change for MV Hinship, and that's how the KB changes for a normal ship-shaped vessel. Effect of draft or displacement on LCF. Before we discuss that, let's have a look at the side profile of a ship. You see, you have the stern frame of the vessel here and then the overhang of the stern above the stern frame. Now, if you see as the draft increases from here to this place, there is only a slight change in the water plane, a negligible change in the water plane. But as the draft rises from here to here, there is an addition of greater water plane area which is continuously increasing from this draft to this draft in the after part. And then the water plane area becomes more or less again the same. So what do we see? That here when the draft increases, initially the water plane area does not change much. Then there is an increase, but the increase is because of the increase in the water plane area near the stern. And when there is an increase in water plane area near the stern, that will cause the geometric center of the water plane area to shift aft, that means towards the after perpendicular. LCF is the longitudinal location of the center of flotation, usually referred to from after perpendicular. Center of flotation is the centroid or the geometric center of the ship's water plane area. For an intact vessel, water plane area is the area occupied by the vessel at the water line, which obviously, as we discussed a while back, changes with draft. Thus, as the draft or the displacement increase, change in LCF depends on the change in the shape and size of the water plane area. And we have already discussed that waterplane area near the stern will gradually increase as the draft increases, thus causing a shift in the centroid towards aft and hence a slight reduction in LCF. For typical ship-shaped vessel, the change in LCF with draft or displacement can be shown as in this diagram. We have the scale 69 meters here, 73 meters here. This graph is typically for MV hinge ship, but shall hold good for any normal ship-shaped vessel. What do we see initially? As the draft increases, LCF is more. That means centroid is towards the forward of midships. Then it is more or less same because the waterplane area remains more or less same. Then as the waterplane area, because of the overhang, gets added in the after part, it causes a shift in the center of flotation towards aft and hence a reduction in the LCF, and thereafter it again becomes more or less steady. Effect of draft or displacement on LCB. Let's again have a look at the side elevation of a vessel. What do we see here? And how does the volume of displacement or underwater volume change as the draft increases? Well, of course, the underwater volume will increase. But what will be the increase pattern in the vertical direction, which will affect the KB, which we have already discussed? And how is the change taking place in the longitudinal direction, which is more important as far as the longitudinal location of center of buoyancy is concerned? Now we see from here to here, as the draft increases, the volume of buoyancy is increasing, but it's increasing in the vertical direction. There is no significant change in the longitudinal direction. So we don't expect much change in the LCB. Slight change, of course, would always be there. Not too much of a change in the LCB as the draft increases from here to here. But any further increase will add this overhang volume to the volume of buoyancy, thus increasing the volume of buoyancy near the stern and, like center of flotation, causing a shift of center of buoyancy closer to the after perpendicular. So LCB is the longitudinal location of center of buoyancy, usually referred from after perpendicular. COB is the centroid or the geometric center of the ship's volume of buoyancy. Volume of buoyancy is same as volume of displacement, and which is for an intact ship same as underwater volume. Thus, as the draft or displacement increases, change in LCB depends in the change in shape and size of the volume. As already explained, the size is going to continuously increasing, and any change in the vertical span or vertical direction of the shape will cause a change in KB, which we have already studied. How does this volume of buoyancy change in the fore and aft direction? For a typical ship-shaped vessel, the change of LCB with draft or displacement can be seen as per the following graph, which is actually for MV hinge ship. And what do we see in this case? The LCB is slightly higher here. It gets little higher. So there is a slight change from here to here. In this case, moving little forward, that means LCB is increasing. And then LCB starts decreasing. Why? Because with the addition of this volume of buoyancy in this part as the draft increases, the B tends to shift aft, thus reducing the LCB. So from here to here, yes, there is a slight change, very insignificant change. Then there is a reduction in LCB, and this is how the LCB changes with change in draft or displacement. Effect of draft or displacement on KMT. Now KMT in the hydrostatic particulars is the vertical distance of the initial transverse metacenter. Please pay attention to the word initial. Initial transverse metacenter means transverse metacenter of the ship in the upright condition. When a ship floating at rest in still water is upright and is transversely inclined by an external force through a very small angle d phi, the center of buoyancy of the ship shall shift to the lower side. The point where the new line of buoyancy in this inclined condition intersects the earlier line of buoyancy in the upright condition. And what was the line of buoyancy in the upright condition? It was the center line of the ship. So the point where the new line of buoyancy through the center of buoyancy in the inclined condition to angle d phi meets the center line, that point is referred to as initial transverse metacenter. Word initial is very important here because metacenter keeps shifting with the angle of heel. And what is in the hydrostatic particulars is the height of the initial metacenter from keel, the kmt. Kmt is equal to kb plus bmt. What is bmt equal to? It is I upon v, where I is the moment of inertia of the water plane area about a fore and aft axis through the center of flotation, and v is the volume of displacement. Now, based on the cumulative effect of change in kb and bm transverse of the vessel in a typical ship-shaped vessel, the change of kmt with draft and displacement can be shown as it changes for MV hinge ship, and the change can be shown by this draft. We have, what do we see? As the draft is less, the value of km is high, it's 12 meters or more. It is reducing as the draft is increasing, and then the change becoming very less. So this is typically how the kmt of a ship-shaped vessel shall change in the hydrostatic tables. Effect of draft or displacement on KML. KML is the vertical distance of initial longitudinal metacenter from keel. The word initial is again very important. It's the longitudinal metacenter of the vessel in the even keel condition. So, initial MT is the transverse metacenter when the vessel is upright. Initial ML is the longitudinal metacenter when the vessel is on even keel. When a ship floating on even keel is at rest in still water and is longitudinally inclined by an external force through a small angle d phi, its COB will slightly shift forward or aft. The point where the new line of buoyancy through the shifted B intersects the earlier line of buoyancy passing through the center of buoyancy in the even keel condition is denoted as longitudinal metacenter. KML is equal to KB plus BML. BML is equal to I upon V, but I here is the moment of inertia of the water plane area about an athwartship axis through the center of flotation. So here this axis has changed. It was fore and aft for BMT, it's athwartship for BML. V is the volume of displacement. Based on the cumulative effect in the change of KB and BML of a typical ship-shaped vessel, the change of KML with draft or displacement can be shown as per the following graph, which of course is for MV hinge ship, but will be applicable to any normal ship-shaped vessel. We have KML on the x-axis, we have draft or displacement on y-axis, and the graph is typically like this. It's quite high when the draft is low. It reduces as the draft increases, and then it is more or less steady with very slight difference. This is the graph which represents typical variance of KML with change of draft or displacement of the ship. Now we come to end of this video. If you like the effort worth commenting and liking, please do like the video, share your comments, share the video with your friends, subscribe to the channel if not already done. Wish you all a very happy learning. All the very best. Thank you very much.